Before we go into lesson 4, it's important for everybody to make sure they know how to read a chemical formula. And there were some formulas that you had to read last week, but in this case, we're going to be looking at more complicated formulas. So we want to make sure you guys remember how to do that. So easiest one that we've looked at before, our weird quarantine break slash schooling, and we've looked at last week in your assignments. I believe it was in lesson 3. So when we're reading the formula for water, we're looking to find out how many atoms are in that molecule. One thing that we do is we look for how many symbols, how many atomic symbols are in the actual formula itself. That tells us that we've got 2 different kinds of atoms happening. The number that's next to those, this one here, the little baby subscript number, helps us to figure out how many of the atom to the left we actually have. So that number there tells us how many hydrogen we have. So over here we don't have a number. Over here we don't have any number at all. But just like in math, sometimes we don't write the number if the number is 1. It works that way for science too. Sometimes we don't write that number, but the number is always 1. So we just assume that there's 1. They wouldn't have written the symbol if there wasn't at least 1 of that atom in the compound. So we've got 2 hydrogen and 1 oxygen atom. So we might be asked just that, how many hydrogen atoms are there? We would just say that there are 2. Or we might be asked how many atoms total. In that case, we'd say 2 from our hydrogen and then 1 additional from our oxygen, and we'd say 3. Reading any kind of formula works the same way. Some of them, like I said, are just more complicated than others are. Carbon dioxide is a pretty simple one. So in this case, I don't have any number next to carbon. Now, where people get tricked by this one is they forget that these are 2 separate elements. They combine them together just because of the way that they're written. Carbon, is its own atom. Oxygen, is its own atom. So we read them separately. For carbon, we do not have any number down below, which, like we said, for oxygen, just lets us know that there's 1. Anytime the number is missing, we know there's 1. And for oxygen, we've got the little number, and to the left of it is the oxygen, so we know that it applies to the oxygen. So in this case, if we're looking just at total atoms, we've got 1 carbon, we've got 2 oxygen, for a total of 3 atoms. And again, we could break that down and look at the atoms separately, and the number of oxygen, the number of carbon. But if we're looking at total atoms, that's what we've got in that molecule. I hope that helps. Okay, we'll move on to lesson 4 then. I apologize for my sniffing. My allergies are getting the better of me. In lesson 4, we started out with that idea of chemical formulas because we're going to be looking at reactions. And lesson 4 is all about chemical reactions. Chemical reactions take place or occur when the bonds between atoms break apart and rearrange. So kind of a complicated statement there. But if we go back and we think about our ball and stick models from last week, in this particular one here, I have carbon in the middle. That's what the black ball represents. And then I've got 4 hydrogen around the outside. So if this little atom here, this molecule here, were to go through a chemical reaction, maybe one of the things that would happen is that it would lose one of its hydrogen atoms. So we would be left with something different than what we started with because of the movement of that hydrogen atom. And maybe something takes its place, maybe it doesn't. Just depends on what kind of reaction you have happening there. But we have something different than what we started with. So we started with our 4 hydrogen bonded to the carbon, and we end with a missing bond and 3 hydrogen attached to the carbon instead. So that's kind of what the definition means, is we're going to start with one thing, we're going to disconnect and wiggle those atoms around, and we're going to end up with something different than what we started with. Basic idea of a chemical reaction. When we write those chemical reactions, that's where we use those formulas that we were looking at back in lesson 3. So in the formulas we're looking at, we have something that we start with. We have a process that happens, which is what that little arrow represents. Some kind of energy coming in, some kind of process taking place. And then we end up with something new. So in this case, it would have been our atom here, would have been on this side is what we started with. Something happens, in this case, my hand ripping the bond off, and we end with something different than what we started with. The names we give to those help us to keep organized, help us to know what we're talking about when we're looking at these different kinds of reactions. So this guy, these guys over here are the reactants in our formula. So whatever we put on this side together is what we're starting with. So it could be 3 different atoms together, 3 compounds, 3 molecules of a compound. It doesn't make any difference what it is. This is the side where we find the reactants. This side instead is where we find the products. So the reactants react to produce the products. That's how I remember what's where on the table. The reactants react to produce the products. Have no idea if that helps you or not. If it does, great. If it doesn't, feel free to wipe it from your mind. You can only be scarred so many times before you carry it over there. So now we have to make things more complicated, because sometimes when we're looking at the reactants and the products, they don't only need one compound in order to make a reaction happening. So if we go back again to this little guy here, this is just one molecule of a compound. So this might not be enough for a reaction. You might need more of it. Think about it just like pouring it into a cup. Sometimes we need more of it in order to get things going, to get the reaction happening. Well, that means we have to have a new way of showing the number of compounds, the number of molecules that we have, so that we can read those in our formula when we're looking at it. So we have to talk about a little number called a coefficient. So coefficient, there was one of them actually in the reading that you did on photosynthesis. So the first part, I'm just going to write out the reactants for photosynthesis for us to see this. So there was a 6 out here in front, which is the number we have to talk about here. We've got our CO2 that we start with, and we combined it with some water. But you see that 6 showing up again here. That 6, each of them on both sides there, is a coefficient. So this guy here and this guy here are called coefficients. Okay, I'm not good at talking and spelling at the same time, so hopefully that's right. I'm sure one or more of you will let me know if it is incorrect. So when we're looking at the coefficients, you can think about it like a number that tells us how many of this molecule there are. So we've got a molecule of carbon dioxide here, but we need 6 molecules of carbon dioxide in order to make this reaction happen. So we would have 6 of those instead of just 1 of those. So on this side here, we've got 6 as well. So we'd have 6 H2Os instead of just saying we have H2O. We're going to have 6 of that same molecule. But that means we have to do the math a little bit differently to figure out how many atoms we're starting with. That's where the tricky part comes in. So we're going to get rid of some of this extra down here. And we're going to look at how many of each one of our atoms we've got in the overall chemical reaction. So all of this is our reactants, remember. So everything here, we're looking at the reactants. This is the beginning of our process in our chemical reaction. So something's going to happen to these guys to make something new. So what we want to know is how many of each one of the different kinds of atoms we're starting with. Because remember, our matter is going to be conserved. We're going to have the same amount of stuff at the beginning that we have at the end. And it's a way to double check that you've written the equation correctly is to look at those numbers, because a mistake in your writing changes the whole formula that you're looking at. Over here then I can see I've got carbon, I've got oxygen, I've got hydrogen, and then another oxygen here. So the 3 atoms that I'm looking at are carbon, I've got oxygen, and I've got hydrogen. I'll put hydrogen over here. I think about all of this as a math problem when I'm looking at it because of my little numbers, my unseen numbers here. I've got that little 1 that's down there below the carbon. So I know that there's 1 atom of carbon here, but I also know that there's 6 of this molecule. So I'm going to write down this number 6. And I've got carbon 6 times. So inside here, I'm just going to write down that carbon. The answer tells me how many of those I have. So in this case, I've got 6 carbons. So 6 is the answer. Hydrogen works the same way. In this case here, I've got 6 water molecules. So I've got 6 H2s. So I'm going to write my 6. I'm going to write my H2. And I'm going to do the math, my 6 times 2, to get 12 total hydrogens. And most people truly do not write this out on a piece of paper. They just see that they've got a 6 and they multiply by the 2 and they know that gives them 12 hydrogen. This is just one way to look at it if you're not seeing it for yourself. Most people, if they catch on to the math of it quick, it's not a big deal to calculate the number of atoms. But if you need it traced out, this is a way to do it. Oxygen's a little bit tricky because we find it in 2 different molecules here. Over here, we've got CO2. We've got 6 CO2 molecules. So for writing it the way that I've been writing it, we're going to put our 6 first again. And I've got 6 of that oxygen molecule there. And what I'm going to do is write it just like a math problem. I'm just going to add what I've got in the other side of the equation here. So in this side here, I have 6 oxygens, but just single oxygens. So I'm just going to write my 6 again and put my O with it. So over here, I've got 12, 6 times 2 oxygens. Here I've got 6 oxygens for a total of 18. So now I know when I'm looking at this equation that if I'm conserving matter the way that the article said you should, that you should have at the end how much you started with. Whatever you've got at the beginning is what you've got at the end. I should have 6 carbon atoms at the end. I should have 12 hydrogen atoms at the end, and I should have 18 oxygen atoms at the end. And they're going to be in different locations and make different things, and that's okay, but they still have to be there. They have to be somewhere in that part of the reaction. So let's look at that part of the reaction, and we'll look at the products in this case. The products are just the result of that chemical reaction. So we're just going to look to see if the number of atoms is the same as it is with what we started with. If it isn't the same, some kind of error happened. Whether there was a measurement error, whether there was just a typo that somebody wrote something down incorrectly, something went wrong and it has to be accounted for. So making sure that you've done this correctly really saves you a lot of extra work in the long run. So this guy over here, C6H12O. So this is the sugar that we end with after photosynthesis. We start out with the carbon dioxide in the water. Light is involved in the chlorophyll of the plant. We end up with sugar and with oxygen. You'll notice we have another coefficient come back with our oxygen this time. Nice that we don't have any over here, because this would have been some pretty messy math if we had. So we're looking for these numbers, just like we said, these numbers, we want them to match what we started with. So what we want is to have, let's see here, what was it? We want it to have 12 no, 6 carbons. We want it to have 12 hydrogen, and we want to find 18 oxygen. And so that's what we're trying to find. That's how we will know that matter was conserved, that we have all of the same atoms that we started with. So we'll start out here with carbon. We'll do oxygen just like we did before, and hydrogen as well. So carbon, I don't have any coefficients, so I don't have to worry about any kind of multiplication at all. All I have to do is write down the number. The number tells me how many carbons I have. So for this guy here, I've got 6 carbons. For hydrogen, same thing. I don't have any coefficient, so whatever number is next to the hydrogen tells me the number of hydrogen that I have. I've got 12 hydrogen. Oxygen, I start out easy. I've got 6 oxygen here because I have no coefficient shown. So 6 oxygen. On the other side, I've got a coefficient here. So I have to do the multiplication to get the answer on this one. So I've got 6, and I'm going to multiply by my 2 oxygens. So in this case, my 6 times my 2 gives me 12, plus another 6 gives me 18. So the happy news is that we've got a number of atoms in our product that matches the number of atoms that we started with. We started with 6 carbons, we ended with 6 carbons. Started with 12 hydrogen, we ended with 12. Started with 18 for oxygen, we ended with 18 again. And you can do that for any chemical reaction, for any process that you're looking at where you're conserving the matter that you have. You should be able to see that what you have at the beginning is what you end with as well, even if it looks different, if it's put together in a little bit different way. So there is a lovely example for you. There are lots more to go over on your homework assignment. So get to them before it runs out of your brain. Have fun.